Okay, so let's think about a particular example of a very easy function, a very familiar function we all know and love. This is the identity function, the function that just gives you back whatever you give it. So its graph looks like a line, and we could ask ourselves, what's that doing as x increases without bound? In other words, what's the limit as x goes to infinity of this function f of x? But of course, f of x is nothing more than x itself, so again, we get to one of these obvious limits. As x increases without bound, x increases without bound. We're going to write that as the limit as x goes to infinity of x is infinity. I want to point something out here, and it's a little bit subtle. This function, x, as x goes to infinity, has no limit, right? It is not settling down near one particular value. The limit does not exist. It's perfectly reasonable to say the limit as x goes to infinity of x does not exist. So when you write that a limit equals infinity, what you're saying is that the limit doesn't exist, but it doesn't exist in a particular way. Okay, so that's pretty confusing, right? We write that this limit equals infinity, but then we say it doesn't exist. Why on earth would we do that to ourselves? The answer is that there is a particular sort of arithmetic of this symbol infinity. Remember, infinity is not a number, so this symbol will not obey all the rules of arithmetic we're used to, but it will obey some of them. Here's one rule of the arithmetic of infinity. If you take infinity and you add any number to it, you should get infinity. I put this in quotes because you shouldn't take it literally. This is sort of a figurative statement, and what it really means when we unpack it is that if I know one quantity is going to infinity, another quantity is going to L, if I add those two quantities together, the sum is going to infinity. Where does the infinity plus L come in? That's exactly because we're taking the limit of a sum. We expect the limit of the sum should be the sum of the limits. In this case, that looks like infinity plus L. There are several additional rules of the arithmetic of infinity. I'm just going to write them down. It's a good idea for you to try to translate each of these figurative ideas into a literal statement involving limits, just like we did here in black for infinity plus L equals infinity. There are some arithmetic operations with infinity that you need to shy away from, and those are these following three forms, known as indeterminate forms, and that basically gets to when you're comparing an infinity to an infinity. So if you're asking infinity minus infinity, what's that? You're comparing infinity with infinity in the sense of distance, in the sense of subtraction. Same thing with division is one way to compare them. And then 0 times infinity, well, 0 is really small, infinity is really big. Which one's bigger? Which one's smaller? Who wins? Those kinds of questions, that's sort of a comparison. Those are called indeterminate forms. Let's give an example of what to do when you see one of these indeterminate forms. So consider this quotient. This is a rational function, x squared over 2x squared plus 7. What's happening as x goes to infinity? Well, as x goes to infinity, x squared goes to infinity. And as x goes to infinity, 2x squared plus 7 goes to infinity. So this thing looks like infinity over infinity. That's one of the indeterminate forms, so we have to do something else. What we're going to do is multiply the expression inside the limit by a form of 1. In this case, 1 over x squared divided by 1 over x squared. Why did we pick x squared? Well, we wanted to kill that x squared going to infinity. When we do the algebra, we'll end up with 1 over 2 plus 7 over x squared. That has nothing to do with limits, that's just algebra. Well, we know this limit, the limit of 1 over x squared as x goes to infinity is 0. The limit of 7 over x squared as x goes to infinity is therefore 0. So we end up with 1/2. This might tempt you to ask, is infinity over infinity equal to 1/2? But if you do the exact same computation with a 3 in place of a 2, the limit you compute will be 1/3, which would lead you to ask, is infinity over infinity equal to 1/3? The answer here is to not assign a value to infinity over infinity. Does that mean you should give up? No. What it means is, when you see an indeterminate form, your work isn't over. You still have work to do. What we need to do then is do some algebra, as we did here. In this example, we did some algebra, right? Well, we had to be clever about which algebra we did so that we made sure we were doing the right thing to give us an answer at the end of the day. But the point is, if you see infinity over infinity, or 0 times infinity, or infinity minus infinity, that doesn't mean you throw your hands up and walk away. It just means you have to try something. What kinds of things can you try? The first thing we could try is the one we just did, which is to multiply or divide the numerator and the denominator by the same thing. You'll have to pick what you multiply and divide by so that it takes care of the problem, right? So that it takes care of the infinity. That's why we picked 1 over x squared, because the kind of infinity we had on the top was an x squared kind of infinity, so we needed to kill it with an x squared kind of infinity. Another algebra trick is called multiplying or dividing by the conjugate. This is useful when you have things like square roots. Okay, you can't subtract square roots. There's no nice formula for that. But the nice thing about a difference is if you multiply a difference of two things by the sum of those same two things, you end up with some squares. In this case, the squares we end up with are the squares of the square root of x plus 1. So the square root of x plus 1 squared is x plus 1, and the square root of x plus 2. Now notice what happened. In the numerator, x, which was going to infinity, well, we've canceled it. We had an x minus an x, and it goes away. So we've gotten rid of an infinity from, in this case, the numerator. Sometimes you get rid of the infinity from the denominator. We observe that using the fact that infinity plus 1 is infinity, and that the square root of infinity is infinity, both terms of the denominator go to infinity, and then we know that the infinity plus infinity is infinity. So what we're left with looks like minus 1 over infinity, and I've put that in quotes because you should remember it's only a figurative statement. But what that tells us is this limit is 0. There's one more standard trick. It works when you're computing limits even if you're not dealing with infinity, but it really shines in this context. And that's to squeeze the thing you're taking the limit of between two functions that you know the limits of. Now, in the previous example, we actually considered this limit of 1 over root x plus 1 as x goes to infinity, and I sort of brushed past it without thinking about it. But let's actually compute this in a sort of a hard-nosed way so we know that we're right. The idea behind squeezing is you want to compare this function, 1 over root x plus 1, with a function you know something about. In other words, a function that's maybe a little bit simpler, that you have a better handle on. One fact we know for sure, one comparison we can make, is that the square root of x plus 1 is always bigger than the square root of x. So if we take reciprocals, we get the opposite relationship. Okay, that's good. That tells us that we can compare this function, 1 over root x squared plus 1, to a function 1 over root x, which maybe is a little bit easier to deal with. In fact, we know exactly what's happening to 1 over root x. It goes to 0 as x goes to infinity. Now we need to make one more comparison, which is that 1 over root x plus 1 is always positive. That seems pretty clear. And we know that 0, being a constant, goes to 0 as x goes to infinity. So let's combine those two pieces of information together. 1 over root x plus 1 is squeezed, or sandwiched, between 0 on the one hand and 1 over root x on the other. Now we know that 1 over root x is going to 0. We know that 0 is going to 0. Well, what could possibly be happening, right? It's always between those two, and those two are both going the same place. So it must also go to 0. This idea is sometimes called squeezing, sometimes called sandwiching. My favorite name for this, though, is two policemen and a drunk. So these two are the policemen. And you imagine, drunk people don't walk straight, right? We can't really predict their behavior. But as long as you've got a policeman on both sides of the drunk, and the policemen are both walking to the station, well, the drunk is going to have to go to the station too, no matter how unpredictable the drunk's behavior.